to another Neurotech San Francisco Hack Night. NeurotechX is an international community that facilitates the advancement of neurotechnology. Our pillars are community, education, and innovation. We have chapters worldwide, meetup events, a thriving online community, over 5,000 members on Slack. If you don't have check in your community. You might have a chapter already. If not, get in touch. Let us know. We'd love to help you set one up. Also, check if your college or university has a student club. Again, if not, we'd love to get you started. Definitely join Slack. You can find a link on the meetup page, and you can check out NeurotechXEDU.com for our educational platform for some lessons and other infos. The newsletter you can sign up for, and you can check the job board, NeurotechX Services. All right. So welcome everybody, and yeah, I expect John to chime in at this point and ask some question. he normally does. Should have had one question. So another super busy week. Neuromatch this week, like in itself would be, will take like months to unpack all those talks, as well as the fact that like those are particularly, invasive or, animal invasive, like using a wide variety of tools and techniques that could really use its own, we could use our own workshops to get up to speed to be able to understand all the Neuromatch talks, which were all like super high level too, right? Anyway, jumping ahead, but what else this week on Slack? There's been, I guess the big thing was that we lost premium Slack, and so I don't know if everybody else has noticed, but we've lost a lot of messages, which is super unfortunate because I don't know. So somebody just asked me for a paper that I'd sent them on Slack, but it was enough months ago that they no longer have that reference. And even though I did find that paper before, like I'd kind of like that too. So just trying to see what we got in terms of, I put a link in the agenda for, made a NeurotechX room in the Brain Hack Mattermost. Obviously we've got the Discord that for those that are interested. We've had the Discord for a number of months, and unfortunately it's still not really gotten a lot of traction. I see the Neurable. Is everybody? I don't know if anybody's on the Neurable Discord. They got a lot of activity, I gotta say, which is nice.
I forgot to join it last time. Could you share the link?
Yeah, definitely. It's let me just pull that up. Also at this beginning intro stage, if there's anybody joining for the first time, if you don't mind introducing yourself and tell us what brings you here.
Hi, my name is Will Stonehouse. I'm a club member at the NeurotechX at UCLA. I'm here mostly because I'm interested in listening about how you guys are trying to integrate the mother of all BCI thing with the SSVEP.
Sure. Yeah, no, that's great. Thanks, Will.
Yep.
And we'll definitely touch on that. Is Rashik here yet? I don't see him yet. If fellow Jitzer doesn't mind putting in their name just so that we can know how to refer to you. But yeah, anybody else here for the first time? Do that. Where am I? Oh yeah, here it is. Okay. I'm sending you that, I guess, via Slack, Jaden.
Cool. Thank you.
Do you mind posting this link publicly, if I could, or in the chat or something, so I can get it too?
Oh, sure. Yep. Sorry, I was doing that on my iPad, so let me just get that.
Thank you.
Discord, no problem. Yeah, you know, Nerble, I mean, it's a great company, which the first time I was introduced was actually at a NeurotechX demo days. And yeah, let me just get this. So Will, does the student club have I mean, do you just use Slack or do you have your own? I know that UCSD also has Discord.
Yeah, we mostly communicate through Slack.
Okay.
Through our own Slack.
And are you now missing some history? I mean, how long have you been with NeurotechX, the student club?
About a year. I'm not sure if we have the premium or not.
Well, I mean, I think you're getting it from us.
Okay. Yeah.
Yeah. You know, unfortunately. I mean, I don't know if you saw the discussion, but it'd be rather expensive, you know. I think for what is it, like $6 to $8 per active user, I think. And hey, Diego. Anyway, I put a link for the Vulnerable Discord, and yeah, you know, I mean, they're very, very in line with NeurotechX in terms of working on BCI. Plus, they've hired up a bunch of people that I know I was introduced to through NeurotechX. So Mavi, so Will, Mavi and Sweta actually were the ones that proposed this integration of SSVEP data sets with Moab, and yeah, Mavi's now an engineer at Nerble. So that's a pretty good. Just a sec. All right. Yeah, there's a new Neurotech Pub podcast, which I definitely recommend. That's Matt Angle from Parandromics, and he's John and I were talking a little bit before, and yeah, it's like I don't know what camera he's using, but it's very high quality, and I'm a little jealous, but he's got a great set of guests and talking about you know, obviously talking about BCI, but the Gil is it Gil J is one of the guests who is also the one who did the IEEE brain webinar this week, the brain machine interfaces concept to clinic. That was really excellent. And here, let me. No, that's not the. Yeah, Vikash Gilja at San Diego did this webinar this week. And, one of the things that they were focused on was also, I don't think I've got so if you remember a couple of weeks back was the BCI Awards. And this was one of the, I think it was the winner was the handwriting. Let me, where did they put the winners? Aha, here we go. So the high performance handwriting BCI, so I think it was, I think Francis Willett was one of the guests. But it's Krishna Shenoy's lab there at Stanford. Did you see this, Jaden? The exoskeleton, or I was wondering if the exoskeleton, it seemed very Cynthia Chestic. I don't think she's on that group. Yeah.
Are you talking about from the Neurotech pub?
I dropped in a link for the BCI Awards that was just a couple of weeks ago. Of course, she had a keynote at NeuroMatch this week.
Oh, really?
In addition to I mean, again, NeuroMatch could have been,
Yeah, they packed a lot into that time.
A lot in. I mean, I did catch all the talks. They had 12 presentations for this BCI Awards. I think these were the finalists, and I mean, all super. I mean, just to show you the level that they're at. One of the nominees that was the postdocs that are working on the machine translation of cortical activity to text in Ed Chang's lab, right? I mean, so some really, and then, look, the towards practical MEG BCI with OPMs. If you scroll down to look at the nominees, Matthew Brooks's lab there. So there's some really cool stuff. Anyway, this is the first place was some of the guests that Matt had on the PubTech talk, or the Neurotech pub, and another great show. Plus, he had a whole bunch of other. I think he called them all BrainGate alumni. Let me see what else we got here.
Yeah, I didn't have time to check out the newest episode yet.
Yeah, and let me. Yeah, I the book that I've been reading is this Christian Koch book that it's this integrated information theory approach to consciousness. I mean, this is a group leader at the Allen Institute, and is on all the big papers that mouse, high density recordings of mouse visual cortex and all the incredible work that's coming out of Allen Institute, I still do not understand what integrated information theory is doing. And anyway, but trying to give it one more shot. In that, I think this is his third book on it. Anyway, it got a rise out of John, at least in Slack, but he's unable to follow up this week. And oh, okay, yeah, true. So yeah, anything that people wanted to talk about before we? Well, I won't be able to turn it over to John for Open BCI updates.
Morgan, this is Santosh.
Yeah.
Can you hear me okay?
I can.
Okay. Yeah, I was kind of curious if there has been any traction or any hackathons related to BCI and COVID. Do you happen to know any?
Well, I mean, so I don't know what a BCI and COVID, link would be. There's definitely some work that's going on in terms of neurological effects of COVID.
Yes.
If that's what you mean, yeah.
Sorry, I mean, I was part of this emotive group where we actually networked ourselves with emotive devices and went through a couple of events to capture the data, and it was actually it was at the beginning of the COVID times, right? This was back in April, end of April.
Sure.
So yeah, I mean, there's so many work also evolving, from that. I mean, EEG recording from people during this COVID times. I was wondering, if you happen to know anything along those lines.
Yeah, I mean, so there's reason to believe now that there's enough brain effects. Yes. That it's worth study, right? I know, I want to say it might have been this week or last week, certainly paper, I think a preprint is available from Oxford. That's like, I believe Oxford and then Western in, Ontario, I believe are both, are two kind of like high profile sites that are doing lots of MRI of COVID.
Okay.
And yeah, I mean, so those are two that have like popped up on my Twitter feed or something. But those are both like super high profile MRI sites, right? So it makes sense that they would be looking at it. And they're seeing a lot. Like they're seeing a lot with, I believe, with structural scans, right? Yeah. So if you're seeing stuff structurally, let me double check that. But I want to say that they're seeing stuff structurally, and if so, then the issue is you're really going to need to understand, you're going to need to understand what's happening structurally to be able to kind of like interpret the EEG changes, right?
Right.
I mean, it doesn't mean that EEG is going to be, useless. It just means that it's going to take some integration. Right. But has anybody looked at that? I mean, I know, I want to say like I've seen it from, if we look at like Ed Bullmore's Twitter feed, we'll see, he's at Cambridge, but he works with a lot of London people. Let's see if we can find a quick.
And I was also looking at Open Science Foundation for some data dump on from King's College. They actually usually dump a lot of data.
Well, so yeah, I mean, like there's like OSF is definitely a great place for data archiving.
Yeah.
So that you'll find a lot of stuff there. What are you looking for in particular, like EEG?
Yeah, generally, yeah, EEG for now because that's
sure. So it's funny because actually, I think one of the reasons that I first heard of Mohit, who's going to be our speaker today, was actually finding a link to his EEG data sets GitHub. And as someone who's kept hyperlinks, to show you how old I am, hyperlinks of both publicly available EEG and back in the 90s MATLAB toolboxes for processing EEG. I've followed this a long time, and for a while the EEG lab. Do you use EEG lab?
Yes, yeah, we do. Yeah.
So they've got a link of publicly available data sets. Yeah. But what we expect, and this is in conjunction with the Schwartz Center that Scott McCaig's lab that produces EEG lab, has a grant with Open Neuro's Russ Poldrek's group that also produces Open Neuro to have EEG MEG hosted at Open Neuro. I think it's actually under some other name like NEMAR or something.
Okay.
But if you just go to Open Neuro and put EEG into the search field, you'll get a number of
Yep.
So Mohit, if you don't mind jumping in early, do you have anything to say about publicly available EEG?
Yeah, sure. I was actually thinking of adding that at the end of my presentation as well, because I thought I made that repository because I spent when I started working in the field of BCI, I spent a lot of time looking for the data sets. And as you mentioned, that EEG lab and those SCC and UCSD website, they have this web page available where all publicly available information is there. But I felt there was a lag that we cannot update. Basically, I'm collecting data. A lot of other researchers in this community are collecting data, but we're not able to update it in that one single repository page or somewhere where everybody of us can see it and use it. So
sure.
So
you keep that pretty up to date, or that's still an active project for you?
Yeah. I try to keep it very up to date, because whenever I'm reviewing other neuro papers, or when I'm just reading some neuro papers for myself and I see this particular author has shared any data set, or I find any new data set, I try to add it in my repository. But I recommend all of you as part of the NeurotechX community members and other people who see that repository too, because it's open repository. So I would be really happy to add anyone as the contributor. So awesome. Anyone can propose changes in that, add more and more data sets, bring and make it a really awesome, information rich repository, right? That was my goal with it to start with.
I love it. Yeah, I mean, we need something I don't know if you ever check out Papers with Code.
Yeah.
But so it's a cool machine learning, list. And papers with data, right? I mean, because it's these days it's basically trolling through, bioarchive or something, finding EEG papers, and then they're most likely these days very likely to have some publicly available data, but that's not going anywhere. Yeah.
So I'm gonna post Physionet. I don't know if anybody.
Sure.
knows.
Sure.
Yeah.
Yeah. I mean, Physionet's good, and honestly, Physionet has been around for a long time.
Yes. Yep.
And yeah, I mean, so like at least before Temple University Hospital released their data set, Physionet was like the place to get epilepsy data.
It is.
There was like a group in Freiburg. There was a European site that like had data, and then now they charge. I don't know. They want like 3,000 euros or something. It's yeah. I don't know. Anyway, Physionet's great, and obviously they're the ones that host what's that one data set that a lot of people use. It's like EEG BCI or something like. Anyway, it's certainly got the BCI data sets that actually UCS the student club, the UCSD NeurotechX student club has got a Kaggle competition using data set 4. I think they're using like 4.2b, if that makes sense to people. And
I also try to curate all the links for all the data sets.
Oh,
So
okay.
that's my post. Blog.
Okay.
So,
Okay.
I collect a lot of EHR data and NFL punting analytics data. So
Sure. And I mean, you've already seen Open Neuro.
yeah, I did. I was kind of interested to know more on the COVID situation linkages right now. So that's where.
Yeah.
Yeah.
So that's a good question. I mean, I know actually somebody that spoke at the BCI Awards.
Mhm.
I know is working on that. He's from Technical University Munich, and he's the if I see his name, sorry, I'm quickly scanning over the list because it's like, yeah, Ziad Tayeb. So this particular guy, now, I mean, this is not this is what their BCI Awards presentation was about. But if you check that first author or get in touch with that first author, like I know he's collecting or he's trying to collect some EEG COVID data.
Oh, okay.
And he's also the Gumpy developer.
Oh.
If I, because I've let me see if I remember. Yeah, it's the same. Yeah, it's the same guy.
Great. Thanks for sharing this. Yeah.
But like I said, like if the MRI results are the way I think they are, then you're going to see EEG changes that are more about the structural differences, or again, like well, do you have any links of any preprints of people trying to do EEG COVID?
I've reached out to some of my colleagues in King's College, so they'll when they get back to me, I'll definitely post them.
Okay, that could be. I think it's King's that Ed Bullmore has been posting about on Twitter.
That's what I was actually. It makes sense. Yeah.
But you got to wonder about something like that causes structural brain effects. Like that's here. I just wanted to put this is Gumpy because I've actually tried to get Zia to come talk about this this Python package too. So, okay, let me
Great.
keep us going. And yeah, so unfortunately, Jaden, I wasn't able to. I'm not able to get to the Open BCI meeting on Friday anymore. Did you catch some of that?
No, I wasn't able to go to this last one.
Yeah, I've got a conflict now. Anyway, hopefully things are still moving ahead. I think we were just kind of waiting on some of the IRB stuff, but everything was in. And
yeah, we have a CLI now, a command line interface.
Yeah, okay, yeah. John said, and so would you say that this is like? I mean, this is. Or is this functionality in Run? Was it
Run Notebooks?
Run Notebooks?
It's Run Notebooks is in the CLI, so you can run the CLI from anywhere as long as you have the environment going. And then if you don't want to pass all of the flags, you can just pass an IP flag, and that'll run the intro prompt and walk you through everything.
So I mean, what's the command name now? Or is it just Run Notebooks?
EEGNB.
Oh, okay.
Yeah.
Okay. I like it. I like it. All right. Yeah, I need to. And any open issues on that in terms of Mac or Linux or?
I mean, not that I know of. I haven't been able to test it on Linux or Mac.
What? I mean, the Linux issue that I had was that, of course, it was asking for sudo when I was going to run it, which
yeah, that's weird.
Okay, you think that's weird?
When you're just running the notebooks?
Well, when it's yeah. I mean, running the notebook to get access to the Bluetooth stream.
Interesting. Yeah, that shouldn't happen as far as I know.
Well, I was thinking that it certainly if you look in, I forget if it's like Muse LSL or it's EG Notebooks itself, but the guy who the last PR on 0.1 that was from somebody working with Blueberry and on Linux, because I was very specific, like our Linux isn't working because of the back end, and there was this issue of like whether you had the kind of like the command line tools that I think HiGat was using was like needed to be a higher priority, and that would potentially take a sudo authentication, or at least that would be my guess. But
I wish I'd still had my Muse to test this.
Oh, okay, right.
Yeah.
Okay. Well, okay, then that's definitely. I never got you the. Sorry, I never got you the Mac screenshot, even though I asked a follow-up question. Sorry.
Also, should I message you in Slack about that free EEG thing?
Yes. Which bit?
About if there's any developer boards left.
Okay, there's one.
Oh.
Yeah. What are you going to use for electrodes?
I have a bunch of open BCI electrodes that they sent me for like other stuff. So,
Okay.
and then I also have some flat silver plated electrodes from FRI.
Okay. Yeah, I'd be very happy. I mean, I need to get back to TMSI, the company that makes the Sigrid, and
Oh yeah.
yeah. I mean, I could. I don't have them yet, but I'd be willing to share those if other people would be willing to use them.
Yeah, that would be awesome.
'Cause I still think that that's a really cool. And did I post this last week in terms of the needless, where it's like they're using the Sigrid, but they're using this like here, let me just
Needless. It's an interesting.
it's necklace, but they've replaced
Oh,
the neck with EEG. I know it's kind of like, you know, like I don't know
it's a
if
little campy.
yeah. But here it is. So there's the needless. I think maybe we talk about it in Paris again.
Oh, this looks like one of those Bluetooth things.
Well, you know what's interesting about this though is that they're not using the TMSI amplifier. They're using the Smarting, the M Brain Train one from Belgrade. And I really want to find out how much one of these things costs, because I'm thinking that it's like it's got to be, you know, pretty reasonable. And yet this is the same system that the ETH Zurich My Leg is the name of like this you know prosthetic startup.
Mm-hmm.
And he won the, I think he won the not the BCI Samara, maybe the BCI Samara hackathon thing, or I'm forgetting exactly, but he was using this quite successfully, or you know had nothing but good things to say about it. And yeah, I think it's like maybe like 1/5 the price of like comparable Neuroelectrics or something.
Yeah, this needless. I'm never gonna be able to say that with a straight face. Looks interesting because I mean, do you really need to buy this $250 Bluetooth speaker?
Oh,
Like, there's got to be a cheaper.
It's funny. It is funny that they go out on that particular item when you know you could get a really low cost, probably similar quality thing for a lot less.
Yeah, it seems like they're mostly using it just for like the nice neck form factor.
Oh, is that what gives them that form factor?
Yeah, that's a JBL Bluetooth speaker.
Oh, it's the neck speaker. Oh, I did not see that. Well, I liked it in terms of where it's putting the weight, right? Because, like, you know, and this is what we were talking about with the kernel flow is like, if you're going to put all that electronics in there, then, you know, it ends up being a kind of like an additional problem in terms like how to both keep it on your head and distribute the weight and like have it not be something you're going to notice if you've been wearing it for 2 or 3 hours, right?
Or 1 hour in my case.
Like I can, you know, like I noticed wearing a hat for, you know, an hour. But I like this in terms. I mean, I still think like having something, you know, like free EG that's just like a pager, you know, that just hangs on your belt would be better if the cable wasn't introducing noise.
I see. Sorry to like, to sidetrack a little, but I see TMSI is also now selling their water-based electrodes.
Yes. Or
Okay, I've been wanting to take a look at those for a while.
is there something better about?
So these are what oh, I can't even think of what they were called now. The company that I bought a Kickstarter from.
I just just so that other people can see this. I still love that the little animations that are going on there for their homepage.
Oh, Mind Effect. That's what it is called. Mind Effect. If you bought their whole kit instead of just the Raspberry Pi with their software on it, they had a headband which used 4 of those water electrodes, and it was supposed to be really good for SSVEP, even with hair, I guess. I don't know. And so I've just been interested in. They haven't had them on sale for a while, and I might pick up.
Sorry, where do you see water?
So here are the inserts. I'm trying to find the.
I mean, when you say water, do you mean like a saline?
I believe it is like you can just dip these things in. Yeah, H2O EEG it says. So just dip them in water. That's what it was so interesting about it. Okay, and so they also have a water-based cap. Here's that.
Okay, I mean, we all agree though that it can't just be, or like sure you add water.
I think we had this conversation like a month ago when we talked about this, and I think we came to the conclusion that it is just water from looking at it. It doesn't say anything about. Let me see.
I know, but like. So what's the
Unipolar
I mean,
EEG
like you see that you roll up this this like I'm gonna call it fabric,
yeah, here are the actual electrodes.
right? So maybe they've put something on that fabric, because
Yeah, that could be it.
like because again, like this is remarkably like the EGI. Or I think they are trying to do a saline. Why am I not getting? Or is it MagStim EGI? No, it's still EGI. I mean, you gotta have some electrolytes. That's
Here, wait, I found another website talking about them, and
I get why they have to do a doll's head for the preterm, but it's a rather disturbing image if you check out the last link.
I'll check it out. But here it says water electrodes are a completely new type of EEG sensor that measures using just plain water. So it's got to be something in the fabric.
It's got to be something in the fabric, right? I mean, it's funny that they don't say anything though, but I'm assuming that okay. Well, I need to get back to them about the C grids,
Yeah.
and those would be. Yeah, I mean the cap looks very conventional, and it's well, you can also get a nice suitcase. I do like it. I mean, I didn't realize that the JBL is actually the necklace itself. but they're kind of you know, I don't want to say gutting it, but yeah, you could easily make your own necklace component. I guess it is nice that you also get the, you know, I mean, what you want is some ability to do sound,
Yeah.
right?
Yeah.
I wonder how they synchronize the clocks between the two. Wow.
That's a good question.
Well, I mean, they are really taking it apart.
They actually do bust it open and get into the
Yeah.
electronics.
Yeah. That's cool, though. So, you know.
Oh, they even disassembled the
And if
amp.
they do, you know, millisecond accurate synchronization of the, or, you know, knowing when they're presenting tones. Again, that, yeah, so Martin Bleichner was working with Stefan Debner previously, but I think like the most recent C-Grid versus high density EEG paper, I think, is Bleckner as the last author now. Just wanted to quickly say that yeah, the hardware hub should be coming online, you know, officially next week. We've got you know, we've still got discounts that you can get through Muse. I mean, for Muse devices, and what else we got here? Unfortunately, we do not have discounts for the OpenBCI, but it's still a good bargain. Let me just pull up. So if you become a member, then and you log into the website, you will get a password to the Shopify, and so this is, you know, a member discount on you know, a couple of consumer devices, but those discounts go to help supporting the NeurotechX community. This is not a for-profit adventure. And again, we'll be hopefully marketing this more widely come next week. Just wanted to see what that. Oh. All right. Okay, with emotive and well, so is the so Santosh, is the Epic X the most recent emotive?
It is, yeah, it is.
Yeah.
Yeah,
Okay.
yeah. I was
So-
like, when you're doing this, I thought I'll also share if there's any discounts. Usually I get some discounts from the motive. Yes, yeah. I'll see if I can actually put that in the chat. Yep.
Cool. Okay. Nothing against that either. Yeah. The I think we'll get a 5% discount. And yeah, this is, you know, we'll be able to talk more about, you know, what we want that money to go to support at NeurotechX. I'd just like to see, you know, getting us being able to provide headsets for underserved communities. Sorry.
Dogs and kids are always welcome.
Yeah. So my daughter's home and the dogs are excited. Okay. Well, so it's 7 o'clock, and I would like to introduce our speaker for this evening, Mohit Agarwal, who's a PhD student at Georgia Tech. And I first became familiar, like I said, with your EEG dataset site, list. But then I was looking at some of your other projects, and these were super super relevant for NeurotechX, at least in terms of how we try to kind of repurpose consumer devices to use for whatever people want to do, but very relevant for actually so the project with OpenBCI, the data challenge that actually Jaden worked on was using BrainFlow originally to get OpenBCI supported in our EEG notebooks, which was originally our way to use Muse systems and get raw data access and synchronized with experiments. So it's using PsychoPy and Muse LSL originally, but now BrainFlow. So we support other devices, including the Neurosity Notion and one of these G-Tech unicorns. So this is just 8-channel system. Anyway, the title of your talk, brain-computer interfaces and machine learning.
Interplay, yeah. Let me actually share my screen, yeah.
Yeah, so please. And I put links to, I believe the archive paper is going to be the most relevant for the talk today.
Right, yeah. That one is the most relevant, I think. Is everyone able to see my screen?
I can.
Okay, perfect. All right, yeah. So I'll start. So first of all, I think, thanks Morgan for inviting me to the NeurotechX Hackathon night, right? And so we have been working. I work with my advisor is Professor Raghupati Sivakumar. I'm a PhD candidate at Georgia Tech, and we have been working on brain-computer interfaces for the last, I would say, like around 6 years. So this was like around like when I joined as a PhD student, we started basically this field in our lab because our labs mainly works in the domain of wireless communications and mobile computing. And my research advisor was mainly interested in like taking the wireless communication or like communication in general to the next level, which is like basically thought-based communication. And there we have like the brain-computer interfaces. So that's the story of how I started working on brain-computer interfaces. And I would say, like initially I started working with a little bit of motor imagery-based projects, like developing systems in which a person would be able to communicate to their smartphone or their laptop just by thinking about moving their left hand or moving their right hand. And then from there we developed a lot, and tonight I'll be giving a little bit of overview of all the research work that I've done over the last couple of years. But most importantly, I would be focusing on this last piece of work that we were working on for the last two or 3 years. And it's a very interesting and exciting work, which is like the basic premise of this work is how can we use the EEG-based brain-computer interfaces to actually help the machine learning algorithms. So, all right, so I'll start with a little bit. I think everyone here is familiar with the brain and EEG, but still I would like go quickly over the basics, which is like we know the brain, it's the most complex organ in the human body. It produces our every thought, action, memory, feelings, and experiences of the world. And there are like billions of neurons sitting inside the human brain, and each of these neurons are communicating with each other through electrical impulses. And these electrical impulses are the result of the chemical activities that are happening inside the neuronal cell body, which basically hyperpolarizes or depolarizes the cell membrane, resulting in the generation of electrical activity. And EEG, as we all know, is basically the digital capturing of this electrical activity. Since we know there are different parts of the brain associated with different kinds of activities. So for example, like if I get the EEG from C3, that would reflect as like motor and sensory functionalities of the human brain. EEG specifically measures activity of billions of neurons instead of single neuron. There are other methods to compute the electrical activity from the human brain, namely intracell recordings, fMRI, FNIRS, MEG. But we in our lab specifically use EEG because of its non-invasive nature, low cost, and portable nature. Machine learning, I'm pretty sure like everyone is very familiar with the unprecedented use of machine learning in today's industry. It has the capability to learn the hidden structures in the large and unstructured data sets. There is a good correlation between machine learning and I would say brain, which is because parts of machine learning were inspired from the human brain, like basic perceptron design, which is mimicking the functionality of biological neuron. A lot of people would have like arguments against it as well, but let's go with the flow. And then there's also convolutional neural networks which are directly derived from the vision processing inside the human brains. And in the last decade, we have seen a surge in terms of the capability and applicability of machine learning algorithms in almost every field of science and engineering, owing to the availability of GPUs, various open source libraries like CUDA, Torch, TensorFlow, and also massive and huge data sets like ImageNet. We have seen some really interesting architectures like generative adversarial networks, which are capable of generating data, and state-of-the-art achievements have been done in recognizing images, reinforcement learning in games, and also in machine learning, machine translation, or natural language processing tasks using BERT or other architectures. So EEG have been existed for the last 100 years. ML is quite old and has become quite powerful and applicable across various domains of science and engineering. So we are particularly interested in the interplay between the EEG and ML algorithms. And we see this interplay at 3 different levels. At the very simplest level, we see ML or machine learning as just a tool, or rather a very powerful tool, to learn and characterize the brain activity of an individual to build meaningful applications with it for the day-to-day use cases. For example, thought-based communication devices, wake-up command design for VBCI variables, or like the people must be familiar with this work of Facebook, which is they are trying to detect the intended speech from brain activity in real time. Oh, and I should add that I'm like trying to do a informal talk, so feel free to interrupt me at any time with any kind of questions, or like even if you guys find anything wrong in my presentation, just feel free to interrupt me. And any kind of feedback is always appreciated.
Sure.
All right. So moving on. So the second level at which we see the interplay of machine learning and EEG is we rely on EEG as the alternative input to the machine learning algorithm. So currently, machine learning algorithms use or explicit data like ratings and reviews, feedback, or user actions basically as input. So we think like if we provide user thoughts or like directly the brainwaves as the alternative input to the machine learning algorithms, that could help us develop the next generation systems. For example, like personalization systems, like recommendation systems for Netflix or Amazon or any other digital media or commercial products, which from human brain waves we can decode what kinds of products or movies or songs a person likes or person dislikes, and how does that change over that time. So that kind of input would be really beneficial for such advanced level systems, or even high precision information retrieval tools. Like right now, when we do Google search or Bing search, we have to use the user actions, but can we rely directly on the human EEG or any other form of brainwaves as the direct input to those search engines or the information retrieval tools? And at the third level, the most sophisticated level is using EEG as the human feedback which is fundamentally helping the machine learning algorithms. So for the learning algorithms that require significant amount of human involvement, EEG can provide feedback directly without putting any burden on the user. So in these three levels, we provide our contributions in terms of first we investigate this interplay between the EEG based brain computer interfaces and machine learning algorithms, and with a user specific focus. Like we design our systems with a specific sense of having the end user as the center part, which I think is missing in general when medical and clinical applications consider the EEG based brain computer interfaces. So for the first level, where we use ML techniques as the tool, as a powerful tool to solve the challenges in EEG processing, we have provided our contributions in terms of detecting eye blinks directly from the brainwaves without any supervision of a human user or without any user training requirement. So it's a completely unsupervised and automatic algorithm. This part of the work has been published in Allerton, and the other contribution that we provided in this particular area is designing a wake up command to increase the battery life of EEG based BCI variables. So we did a study of the currently available BCI variables, including OpenBCI, Muse, and also Emotive Epoch, and some other headsets as well. And we found that there is a major battery life problem with those variables. Like if we are using them continuously, they wouldn't last for more than 3 or 4 hours for a very variable kind of specification battery life. So how
can I ask you? So I'm not familiar with IEEE Allerton. What's the focus of that meeting?
Oh, IEEE Allerton is mainly that is the conference for mainly signal processing side of the part. So digital signal processing in like completely different areas as well, but we publish this work because it's more like a signal processing work. Like we use the
Sure.
Yeah,
and it certainly doesn't surprise me that you're I think it was the Muse S that its big feature is really having a longer battery life, because they're trying to do sleep recordings. But the consumer devices themselves, they're not really expected to be on for more than a couple hours.
Right. And like we thought like that could be a really important feature for the BCI wearables, because as like we are going into this community of having more and more wearable devices, and we see like if my smartwatch power is going down after like every 3 or 4 hours, like my user experience with that smartwatch would drastically slow down or would drastically reduce. So that was the part, like that was a user specific part we were trying to solve with that particular problem statement.
Yeah.
All right. Okay. So moving on, and then at the second level where we use EEG as the alternative input to the machine learning algorithms, we built an algorithm Cerebro, which is able to personalize or specifically rank the commercial items. So we studied this on 10 different Amazon consumer products, and we for this particular task we obtained the data from one of the papers, and then we basically proposed the algorithm of how can we rank 10 different consumer products based on their preferences by relying only on the EEG brainwaves, not like any other kind of input to the machine learning algorithm. This part was published in VSS in 2019. And the third part, which is like really exciting work we have been doing for last 2 years, is how can we use EEG to assist the machine learning algorithm. So basically we propose a novel paradigm to allow humans to assist the machine learning algorithms in a very implicit manner, which accelerates the convergence rate of these specifically reinforcement learning agents. And this part of this work has been published in VSS 20. There's a typo there, I think, and also in one of the workshops in AAAI, which is reinforcement learning for games. And one of the current paper is also under review in neurocomputing. And my focus today will be solely on this part, which is how can we assist the machine learning algorithms with EEG based brain computer interfaces. All right. So this, and also I should add that this work has been done in like collaboration with definitely my research advisor, and there is a new student in our lab group, Ekansh Gupta, and our collaborators who specifically tackles the part of reinforcement learning, Duozu and Professor Fikri. Okay, so we know that today we are surrounded with complex end user applications like autonomous vehicles or self-driving cars. There are applications with robotic control, robotic planning, and robotic maneuvering, targeted advertisements, marketing strategies, recommendation engines we see every day for YouTube, Spotify, Netflix, Amazon, and game playing, Go, StarCraft, chess, all these kinds of games. And the purpose of such systems is to understand the environment and learn to make good sequence of decisions in order to optimize some reward metric. And that reward metric could be revenues in terms of the advertisements, scores in terms of the playing games, or user satisfaction for personalized recommendations or robotic controls. And one of the primary strategy to solve these challenging problems is through reinforcement learning. And I'll explain a little bit about the basics of the reinforcement learning, so everybody is acquainted with the idea of what are the problems with reinforcement learning that we are trying to solve using the EEG-based brain-computer interfaces. And so to understand the reinforcement learning a little bit, we consider a simple problem of playing a famous Atari game, which is known as Space Invaders, as we can see in the right part of the screen. In this game, the idea is for the agent is to recognize the enemy and to fire pretty much all of their enemies by steering left, steering right, and also to save the agent himself from the enemy bullets to score more and more points. So the basic idea is to score more and more points and to live as long as possible in this particular game environment. So in general, reinforcement learning, the agent interacts with the environment by taking an action at time t, and the environment provides the next state and the scalar reward. Reinforcement learning agent learns to map the states to actions in order to maximize this cumulative reward function. And this cumulative reward in the context of our classic Atari game Space Invaders is the total score that the agent will receive at the end of the game. And reinforcement learning is applied to pretty much all of the problems where it is impractical to obtain examples of the desired behavior that are representative of all the situations in which the agent must act. So it is different from supervised learning or unsupervised learning, that like we cannot obtain the labeled example before the training, but we have to interact with the environment and obtain the labeled examples accordingly and improve our policy or improve our behavior to act in that environment. So this is the basic idea of the reinforcement learning. And one of the key elements of the reinforcement learning, to see these key elements, I use this very simple maze game architecture at the right side of the screen. And as we can see, the idea of this game is for the ghost looking agent in this environment. The goal for this ghost looking agent is to go from the starting position to the end position in the minimum number of steps. And that's how the reward is defined, because at every step the agent takes, it gets -1 as the reward. And so in order to maximize the total cumulative sum of rewards, it has to minimize the number of steps. And state in this particular game is defined as the location of the agent. Like if the location is present in this grid versus the location versus the agent is present in this particular grid. And the action that this particular agent can take could be one of these 4 actions: up, down, left, and right. And in this case, no operation or like taking no action is not the possibility. So we consider only 4 possible cases. So in this particular context of the game, we see that the total return or the discounted sum of rewards is basically the cumulative sum of rewards. That if this agent is at this particular state, what will be the total return or total score it will get by the end of the game. That is defined as the total return. And any reinforcement learning algorithm is trying to maximize this total return. The next is policy. So policy is defined as the agent's behavior, which is if the agent is at any particular state, what is the probability of taking one of these four actions, which could be up, down, left, or right. So if it's a probabilistic policy, we call it as a stochastic policy. Otherwise, if it's not probabilistic and like it's completely deterministic, then we call it as a deterministic policy. So here in this particular example, it's a deterministic policy because if the agent is present at this particular grid or this particular location, then the agent will take always up action, and here always up action, then right and right. So this is what we call as policy in the reinforcement learning. The next element is the state value function, and state value function is always associated with some policy. So for this particular policy that we have seen, the state value function refers to the expected return that the agent will get from any particular state. So if we see this particular, the last grid, the right bottom grid, here the state value function is -1, which makes sense because at this point of time, according to this policy pi, the agent will take the right action. So it will get like -1 as the reward, and the game will end. So for this particular state, the state value would be -1. And similarly, we can populate this table for all of these possible agent locations or the state of the environment. So this refers to the state value function. And the next is action value function. Action value function basically decouples the state value function with the actions. So now we have, instead of expected return for a particular state, we now have expected return for the pair of particular state and action. So for example, for this particular block highlighted with yellow color, we have 4 different values which corresponds to taking 4 possible actions. So the agent from this particular state, which is highlighted as yellow color, the agent will get total of -3 rewards if it follows policy P. If it takes the action down, if it takes the action up, it gets -5. And if it takes the right or left, it gets -4. So from here, we can see that the state value function is basically the maximum of the action value function for that particular state, because maximum state value function would give us like expected return starting from state S following policy pi, and then we'll get -3 as the action value as the state value function, because the agent would be moving down. All right. So the next is, after defining the policies, state value function and action value function, the goal for the reinforcement learning agent is to learn the optimal policy. So what is the optimal policy in this sense? In this particular game environment is the policy that we have already seen using the brown arrows, because if we take any other policy or like any other mapping from state to action, that would result in less cumulative score as compared to this optimal policy. So the idea is to learn the optimal policy, or like the way to play any game optimally, and that can be derived if we know the optimal action value function or optimal state value function. So for example, if I know for any game environment, if I know the optimal action value function, which we also call as Q function, then I can just proceed greedily. And by greedily, I mean that I will take the actions for any state. I will take the action which basically maximizes my Q value function for that particular state, and that will define my optimal policy. So long story short, in order to learn to perform optimally in any game, all we have to do is to learn this optimal Q value function or action value function. If we know the optimal action value function, our policy can be derived directly from that, and the agent will know how to behave in this particular environment. So putting all learning a little bit about the reinforcement learning, and then we see that I think like people must be familiar with Atari 2600 games. These were a class of games which were really popular in 1990s for the console gaming. It has around like 526 2D games. Every game has is 210 pixels height, 160 pixels wide, and RGB channel. So it gets 3 foot floating point values from there, and there are total possible 19 actions. And this Atari 2600 has become a standard benchmark to evaluate the reinforcement learning algorithm. So for if we read any papers, anything from like DeepMind or even OpenAI in published in NeurotechX ICML ICLR, using Atari 2600 benchmark to evaluate the performance of their reinforcement learning agents is a pretty common practice. And typically people use, it has like 526 games, but for the benchmark comparison purposes, people use normally 57 games. And I think this is the last bit on reinforcement learning, which is, it's a work from the DeepMind published in Nature in 2015. The idea is to learn the action value function, or like how to play these Atari games using a deep neural network architecture. So this deep neural network architecture has like bunch of convolution layer and fully connected layers. It takes input as the grayscale downsampled image of our Atari game, and it takes 4 frames. So we get like 84 cross 84 cross 4 as the input to this network, and the output of this network is the Q values for all the possible 19 actions. So now if the idea of this network is to learn this optimal state action value function, or no, optimal Q value function. If the network is successful in learning the optimal Q value function, at the output, we will get the Q values for each possible actions. And then we can take action which has the maximal Q value. So that will be able to guide the agent of how to behave optimally in any environment. So I'm gonna skip a little bit on the learning algorithm of DQN, because it is not like directly relevant. All right, so we'll see, here we see DQN in action, like how after training DQN works, or DeepQ network works to train these Pong games or Space Invader games. However, there is a caveat in this. The caveat is the number of samples required to train the DQN to reach at this performance level. So for the Pong game, it takes around 10 to the power 6 frames, which counts as 4 hours or 24 minutes of training, or like 4.5 hours of training if we are playing at the 60 frames per second. But for the Space Invader games, it's more complex game as compared to the Pong. So it takes 10 to the power 7 frames, which amounts to 46 hours of training for 60 frames per second. So the learning based on the learning curves. Yeah, so this is the convergence rate of the Space Invaders on DQN, and we can see that it takes 10 to the power 7 frames to reach up to the score of like around 1500, which is still not very, very optimal, but it's still, it performs really well with 1500 score. And these 10 million frames means the 46.5 hours of gameplay at 60 frames per second. So the summary here is that we know that DeepQ networks or reinforcement learning works really well, but even for these simpler environments, there is a requirement of very large number of training samples to teach the algorithm to play these games. And this is the current problem with the reinforcement learning algorithm, which is known as sample efficiency. And there are 2 main reasons of why this happens. One is the state space of the games is very high dimensional, as we have seen that our games are 210 cross 160 cross 3 are the dimensions of the images. And then we have also 4 frames stacked together, which counts to around like more than 30,000 floating point values. So the state space of these games is very large. And with the very high dimensional state space, the agent has to learn a lot in terms of mapping the state space to the actions that the agent will take. So that is the first problem. And the second, and one of the major problems with the reinforcement learning, is the sparsity of rewards. So these agents do not receive the rewards for a very long period of time. And so, for example, like if we consider the even Pong. So for Pong, like it takes like a bunch of actions in series, but it gets -1 or +1 as the reward only when like it hits the ball or it's not able to hit the ball. And if we see the scale of this problem, we can see, like for example, that games like chess or AlphaGo. In those games, we do not, like, any environment does not give any reward, like whether this move was correct or whether this move was incorrect, until the game ends. Like, so after like a million of steps, we know that whether it's a win or it's a lose, which is like +1 as a reward or -1 as a reward. So for those 1 million steps, agent did not know whether it was taking whether the actions that it was taking was the right, or whether the actions it was taking were wrong. So that leads to a lot of training samples, a lot of interaction with the environment, and that directly impacts the time it needs to train to perform well in those environments. So sparsity of the rewards is mainly the problem that we are trying to tackle with our research. And we can see that human feedback could solve the reward sparsity problem. So if a human is present during the training of the RL algorithm, additional feedback and rewards can be obtained. So this is like a guided training. If an agent is trying to learn to play a chess game, and in between, if there is a human telling the agent that, yeah, you did something right, you did something wrong, that would help the agent to learn faster, just like as another human. So if I'm trying to learn any new game environment or learn any new thing, if there is someone else who is trying to teach me whether I, or trying to tell me whether I did the right thing or the wrong thing, I would be able to learn faster. And this directly applies to the reinforcement learning algorithms as well. And actually we can see it in various application scenarios, like image annotations or captchas. We need a lot of human feedback to train these algorithms to identify what are the statues, where are the mountains, where are the roadblock signs, which is being eventually used for the self-driving or autonomous vehicles. Or like ratings and reviews for the personalization systems for Netflix or Amazon. So they are actually recording this feedback. We might know, we are probably giving it unconsciously or like consciously, like we are providing a written review or rating so that we are being recommended the same kind of stuff the next time. Or like they are tracking, like Amazon tracks how much amount of time I spent on a particular product, like watching it, or if I added it in the cart, whether I removed it from the cart, what kind of products did I buy, what kind of products did I return. So all this is the human feedback at the end of the day to serve the human in order to build a better personalization model for them. And learning by demonstration, this is used in robotic community a lot, I think, in which people show the robot like how to grasp this particular doorknob or how to pour coffee in a mug. So robot sees it and then learns through it. So human feedback, as we can see, is really helpful for these any machine learning algorithms or specifically reinforcement learning algorithms. And this is a very really great work from the DeepMind and OpenAI collaboration, which got published in NeurotechX in 2017. So in this particular work, the authors designed an experimental interface where they provided the GIFs of the agent playing the game. So you can see two different GIFs of which is like 10-second or 1 second. I think, yeah, around like 2 or 3 second of play. Now the feedback was asked from the human observers, whether the left is better or whether the right is better, or whether like it's a tie or can't tell. And this helped the agents to learn, the reinforcement learning agents to learn in a very faster manner. So this is the first potential of how can we use human feedback in the reinforcement learning algorithm. This is the first application where it can help accelerating the learning rate of the reinforcement learning algorithm. And the very exciting part is also the based on the human feedback, reinforcement learning algorithms can learn completely in the absence of reward functions. So in this GIF, which is at the bottom right, we can see that this agent is trying to learn how to backflip. And it is very difficult to define a reward function to say, to give like a +1 or -1 as the reward function if someone did a backflip. But for us as humans, it comes very naturally. If someone is doing a backflip really great, I would be able to say, yeah, you did like a really great backflip. But otherwise, I would say like, yeah, you can improve, or it was not a great backflip. So just based on that human feedback, this agent was able to learn doing the backflip. And this is one of the most prominent problem in reinforcement learning, is like for a very complex environment or complicated environments, it is really, really difficult to define these reward functions. However, for this particular talk and our research, our focus is mainly on learning with the human feedback, but in order to accelerate the learning rate of the reinforcement learning algorithm. So we are still learning in the presence of the reward function that we are getting from the environment, augmented with the rewards or the human feedback that we are obtaining from the human user involved. So the problem with such an approach is like human feedback, we know like from all these works we have seen here, and from all we know that it's really, really useful to accelerate these machine learning algorithms or reinforcement learning algorithms. But it has a caveat, which is basically it puts the burden on the human who is providing the feedback. So that means like if a human is providing feedback explicitly by pressing buttons or using their natural voice, it puts a cognitive burden on the user, and it's not scalable. So I could provide the feedback to a machine learning agent, like any robot or any algorithm, like for 5 minutes, for 10 minutes, but I wouldn't be able to do it for a very long time. And after a while, it affects the usability of these systems. So our focus is on, like we asked this question in our research, if such human feedback can be obtained implicitly without the explicit requirement of taking action. So can human provide the feedback of what they are thinking is the correct action or incorrect action without taking any explicit action, without pressing any keystrokes, or without using their natural voice? And I think, yeah, you must have guessed it by now that brain-computer interfaces, that's how brain-computer interfaces come into this picture. And so it turns out that there is a high-level error processing system in the brain which responds whenever us humans either commit an error or recognize an error. So for example, let's say I'm sitting here giving the presentation and my Roomba robot is roaming around and cleaning the floor. So the idea with the Roomba in my mind is that it should clean the floor completely and perfectly. But if I see Roomba missing like a particular spot on the floor, or missing a dirt spot on the floor, this particular error processing system in my brain would elicit a corresponding reaction. And this reaction manifests itself in the form of specific potentials in the EEG known as error-related potentials. And the error processing system is present. It has like its roots in the evolutionary reasons, because it enables us to recognize the errors that we are committing or someone else is committing and learn from those errors to maximizes our chance of survival. So this error processing system is very strong for evolutionary reasons, and that we can see in EEG as well, because the signal to noise ratio we achieve for error related potentials is really high as compared to any other brain potential. So we use these ERRPs or error related potentials as the implicit feedback or proxy for the human feedback for the machine learning agent or reinforcement learning agent, since it poses minimal burden on the human subject, as no explicit actions are required now from the human subject. So this defines a problem which, in a given human in the loop reinforcement learning environment, can implicitly generated error-related potential from a human observer be detected efficiently, and can it be used for training acceleration in reinforcement learning algorithms? It could be any reinforcement learning algorithm like DQN or A3C or PPO or any other improvements in DQN. So for this particular research, we first developed 3 game environments. These game environments were developed in Python, and we used the OpenAI Gym framework. The resolution was set as 210 cross 160 cross 3 because we wanted to mimic the completely Atari benchmark architecture that I described before. So the first game that we developed is Maze, and for Maze, it's a very discrete navigational system in which the idea for the agent is to go from the starting position to the end position in the minimum number of steps. The screen is divided into 10 cross 10 horizontal blocks, so the agent will move from one block to another block at every time instant. The second game that we developed is Catch, where it's a very simplistic version of Egomania, where like eggs are dropping from the top and there is a bucket in the bottom to catch those eggs. But we removed the complexities from this game of like remove the multiple eggs and consider only one egg, which helps us to monitor the error related potentials in a very feasible manner. The third is a very simplistic game. It's a cursor target game, and in this we can see that one is cursor and one is target. The idea for the cursor is to go towards the target in the minimum number of steps. So, for example, this blue is denoted by cursor. It can move either left or right, but if it moves left, eventually it will be taking a lot more number of steps to reach the target as compared over the other action, which is like just taking 2 rights and reach the target. So these are the 3 discrete grid-based navigational games that we developed in Python and OpenAI Gym environment, and they are inspired from the Atari benchmark. Here we can see that since the screen is divided into discrete blocks, the agent or any parts of the environment moves one step at a time. So for example, in this maze game, this agent would move left, right, up or down at this particular one-time instant. So this would come here and here and here. And for this particular catch game, at every time instant, this bucket can move either left or right or remain at this same position. But also simultaneously, the ball or the egg would be dropping one vertical distance every time instant. And similarly in Wobble, the target is constant, but the cursor moves left to right at every time instant.
Hey, Mohit, Santosh, I didn't mean to interrupt you, but
Oh no, yeah, go ahead.
Is at this point, are you collecting the EEG data, or is it just defining the parameters for the game?
Yeah, so I'll explain that part, like the collecting the EEG data. But yeah, before that, like I was explaining that this is the game environment in which we conduct the EEG experiments.
Gotcha. Okay. Sorry. Thank you.
Yeah. Oh yeah, no problem. I think it's I would love to have this presentation as much as interactive as possible. So okay, so now for these game environments, since we developed it in Python, since we will be recording the EEG data eventually, so we need to have a log of the game. So basically, we are transferring all the state action pairs which the agent is taking in this game over the TCP/IP protocol, which we eventually merge it with a software counterpart, which is known as OpenVibe. We use OpenVibe for collecting the data, so we merge it with the OpenVibe so that our data can consist of all the logs of the agent actions and the states of the states that the agent is encountering at every time instant. So yeah, our experimental protocol is simple. It's definitely IRB approved user experiments. Human observer is sitting in front of the computer screen. So this AI agent is trying to play this particular game environment, whether it is maze or catch or wobble, and at every time instant, the agent is moving one step at a time. The human observer, though, is sitting silently and just monitoring the actions that are taken by the AI agent. So the human observer is not taking any actions, not using their natural voices, just sitting silently and focusing on what is happening inside the game. Every experiment trial, every experiment consisted of multiple trials. Every trial lasted for 100 seconds with 30 seconds break between those trials to ensure that the human observer doesn't feel fatigued and has like proper focus during their experimental tasks.
And how many channels is this, Mohit?
Yeah, so this is 16 channels we are recording. So the device is so the device is OpenBCI board, OpenBCI Cyton board, along with the Daisy board extension on top of it. So that allows us for 16 channels, along with the two reference electrodes, which are the ear clip electrodes. And we use BioPack cap attached with the OpenBCI board. So we purchased the BioPack cap separately. Sorry, did I miss? Yeah.
Is that an inexpensive camp?
Yeah, so this is actually very much in the range of OpenBCI only. So I think I spent around like 500 or $600 for this cap, and this can be easily coupled with the OpenBCI board. Because I like initially I was experimenting with the channels or the electrodes that comes with the OpenBCI board, but it is like I feel for these experiments it's a better idea to have it mounted on a cap, because I think at the time when I started doing the research, this OpenBCI's Ultra Cortex headset was not out. So
Sure.
I was looking for like something which is more rigid and can be just fit instead of like putting like every electrode one by one.
Yeah.
Yeah. So, but before starting the experiments, we also show the user a demo of the game. We ask them to play that game in the manual mode before the trial begins, so that users are properly familiar with what is happening inside the game. So I think, yeah, I talked about the hardware, I talked about the electrode cap, and for the EG acquisition, first I use OpenBCI GUI because it has a really good capability of showing the quality of the data that is coming from the OpenBCI board. So I use first OpenBCI GUI to check the signal quality, and then I use OpenVibe as the final way to collect my data, because OpenVibe allows me to listen to the TCP/IP port, so I can synchronize the labels that are coming from the game, and I can also synchronize this with the raw data. Okay. Yeah. So talking about the synchronization, I think this is one of the major issues if we are working with the error related potentials or any event related potentials, right? And I spent like a couple of months like figuring this out. Like it had so OpenBCI board, I think everyone might have figured this problem out, but it has like synchronization issues in terms of because it uses Bluetooth low energy. So there is a transmitter and there's a receiver, and since it is transmitting the packets over the wireless channel, the packet rate drops, like due to any interference or like any other Bluetooth or 2.4 gigahertz communication going on in the environment, the packet drops. And due to that packet drop rate, what OpenVibe does is like really powerful or not magical, but like I would say powerful. So what it does is, whenever it realizes that there has been packets that are being dropped, it just replaces them with the surrogate packets, which means that it just like copies the previous data. So at the end of the day, like if you have this whole system built up, you wouldn't realize that like why like the data that you're collecting is not working for detecting the error potentials or any other event related potentials, because like you didn't know that this is like packet rate dropping is happening and all those things which are happening behind the picture. So for that, I spent like a couple of months initially, like when I started doing these experiments, figured like I was getting like accuracy of around like 55%, which is like very close to random. And then I thought, what is going wrong with the experiments? Because I was using the state of the art algorithm for error potential detection. It's working perfectly on the public data sets. But when I am doing the experiment using the OpenBCI, it's not working well. So very well. Like long story short, I think I realized that this was one of the major cause, which is the packet drop increases with the distance between the transmitter and radio receiver module. So very simple solution of this: just keep your transmitter and receiver on top of each other and like very close, and it would work.
Yeah, I mean, this is not just an open BCI problem. This is a problem with number of other manufacturers, and yeah. So
Yeah, no, I agree. Yeah.
yeah. I've never actually checked. So is there a way? There's no way to use. Can you use OpenBCI as a wired system?
Yeah, that's a good question. I think like we are trying to figure it out as well, but in order to use the wired system, like I had to change the firmware a little bit and then do like a lot of coding. So I thought like it's just like doesn't count as a research contribution at the end of the day. So yeah.
But okay, but I will. I don't think we've got anybody from OpenBCI with us tonight. Sometimes we do. But I will ask if there's, or I can ask in the forum. I mean, somebody must have done this where they've collected, because I know when we were testing multiple wireless systems.
Yeah.
And we cared about the ERP integrity, and so to really test them, we needed to be sure. I mean, basically, we asked the wireless manufacturers for a way to do a trigger, which is kind of like guaranteeing your TCP/IP synchronization, right?
Yeah.
And when you did that, then you could really identify whether you've got a or what kind of Bluetooth problem you've got.
Yeah.
Okay. So you feel like your success now is good enough. Yeah.
Yeah. So I think like because what I like basically I just did this empirical study of like seeing how many packets are dropping as I increase the distance between the transmitter and receiver.
Yeah.
So basically like I realized like if I put them like on top of each other, then the packet drop rate is very, very minimal, and it doesn't like, so if I keep restarting my device, it doesn't build up. So like if my device is on like for let's say 30 minutes, then it starts building up on that. So
you were doing like 100 seconds.
So every trial was 100 seconds.
Okay.
Every trial was 100 seconds, and then every experiment consisted of multiple trials. So basically I was trying to like restart the whole communication protocol when I'm starting the new trial. And that also gives like, that worked out well in the favor, because that also gave 30 seconds of rest for the subjects, which is like really good for them to take a break like in between the trials, right?
Sure.
Yeah. So I think like I did this first empirical study of like seeing that there is a packet drop increases with the distance, and then which basically introduces jitter. And for any kind of analysis, like event related potential analysis, where we are relying on this specific property that the potentials are synchronized or like time and phase locked with the stimulus, then for those particular kind of potentials, this whole thing would fail. Because like initially when I was working with motor imagery or any or SSVPs, then I did not face this problem, because there is like not the idea of, we don't use this idea of like time locked and phase locked. And then I ran a simulation study, which we can see from the right curve, like how event related potentials or error related potentials are actually very sensitive to this jitter or like this packet, because of the packet drop or like the random offset. And we can see that like even just 100 milliseconds could like impact the accuracy from like around 72% to 65%.
Yeah.
And I think these are like just like couple of things that I learned over the iterative improvements in my experimental protocol, keeping the trial short, so to ensure the focus attention, multiple trials in one experiment with some sort of break, allowing the large number of data samples, user-friendly interface without any environmental or noise distractions, restriction of head movements as much as possible. Otherwise, like it will corrupt the EEG signals and we wouldn't get like what we are looking for. Okay.
So, I mean, when you say that, do you mean something like just like a chin rest?
Oh no. So I keep like the users free. I just like ask them to like not move their head unnecessarily. Yeah.
Okay.
Yeah.
Okay.
Yeah. But I don't like force them in like some chin rest kind of environment. Yeah.
Or worse. Yeah.
Or worse. Right.
So, just a quick follow-up question on this, right? Maybe
Yeah.
I'm not entirely aware of this, but when we use EEG, there's a lot of noise. Are you also referring to some cardioballistic signal noises in this, or is it just more like a packet, dropping? Do you know what I'm saying?
Yeah.
So,
Yeah, so there is definitely like other sorts of noises as well. Like for example, head or jaw movements, eye blink based noises, and like, even the sensor noise, and like bunch of 100 things going inside the brain, which basically acts as the interference and noise. But yeah, but we felt like this was one of the main thing,
mm,
like which was breaking the synchronization, because other noises or other things are like happening randomly and they are not affected by they're not affecting the synchronization or labels, like it's just happening inside, like which is decreasing the signal to noise ratio
okay,
but not adding like any random offset or jitter. Like for example, yeah, like we can say that like if there is a muscular movements, or like if I'm moving my head excessively, then the whole EEG data will be corrupt, so I'll have to like discard those particular samples. So for that particular part, we have some pre-processing in our code, like to see whether there is like a lot of unnecessary movements or like eye blinks to remove them.
yes.
But
What you mentioned on the eye blinks is the number one noise in
yeah,
EEG, but we have used ICA. I don't know if you also have used ICA filtering.
yeah,
Uh,
yeah.
yeah,
Right. Yeah. So I think is one of the main. So for particularly for this ERRP, since we are focusing, as I'll explain like a little bit later, I think like we're focusing on the channels that are coming from like the centroparietal lobe kind of thing.
okay,
So like PZ or FPZ. So PZ, CZ, FPZ, those channels are like not very much affected by the eye blinks.
okay,
But
oh,
I'm definitely sure like if like so currently my processing does not remove the eye blinks using ICA or any other algorithm, but I'm pretty definitely sure that like if I add that pre-processing block, it would also improve my error potential detection accuracy.
okay. So I didn't mean to block you. Okay, so just
Okay.
continue. Thank you.
Oh yeah, no worries, no worries. Yeah. So now let's look at the how does the signature error potentials looks like for the maze game. So here at time t, we have this agent sitting in this particular block, and the correct action for this agent would be to go down, because that would make him or yeah, that would make the agent closest to its goal. But let's say the agent moved to the right at t plus 1.5 seconds. So yeah, I think I forgot to mention in this my experimental protocol that the agent is taking an action every 1500 milliseconds or 1.5 seconds, which gives us enough time to get the data from the user, or like see the reaction from the user. Oh, what is that? Okay, don't. I think yeah, this figure particularly got corrupted. So okay, anyway, this was the waveforms of the error potentials, and it has mainly two components. I think this waveform will also come in the next couple of slides, so I'm not too worried about it. So we have in this particular figure, we had the waveforms of 5 different subjects and also the average over them. And what I wanted to show is that error potentials, as described in the neuroscience literature, it's basically a combination of error negativity and error positivity. So, and all of that comes within the 600 milliseconds of the observation of the error. So there is an error negativity which happens around like this point. It's around like 400 to 500 milliseconds, and then we see a error positivity around 600 milliseconds. So both of them makes our error potential. And this we use the state-of-the-art algorithm for detecting the event-related potentials or error-related potentials. Some people might be familiar about that algorithm. It's really great work from Alexander Bertrand and his team. They won multiple Kaggle competitions using the Riemannian geometry to classify these event-related potentials, and which I'll also cover in later slides. We can see that.
You said this is an Alexander Bertrand algorithm?
Yeah. So this particular, like, to detect the error-related potentials, that's his work. Yeah.
Okay. And what's the publicly available data set?
Yeah, so for this, the publicly available data set is IEEE BCI NER challenge. That was a Kaggle competition that happened. Like, it's again presence of error related stimuli and non-error related stimuli, but it's mainly targeted for the P300 speller.
Yeah.
And that's a really good signal to noise ratio data set. And Alexander's GitHub repository, you would be able to find like the whole codes to process this error related potentials as well. Yeah. Okay. So yeah, looking at the confusion matrix, we can see that we can detect these error potentials with a very high confidence measure. Okay. So now after at this point of time, people might be wondering like why we rely on the error related potentials as compared to the manual labeling. So to answer that question, we ran a quantitative study to compare this implicit feedback, which is obtained via error potentials, over the manual labeling in terms of accuracy, latency, and cognitive burden. So we designed a web-based interface, just like which looks like this. I think it's still hosted, but we are not taking the data anymore. In which we invited a couple of users to Amazon Mechanical Turk to participate in this study. We developed 3 different instances of this of our maze game, which is termed as slow, fast, and faster. In slow, agent was taking action every 1.5 seconds. In fast, agent was taking action every 1.0 seconds, and in the faster, it was moving very fast, 0.5 seconds. And all the subjects had to do, or the humans who have to provide the manual feedback, was to press the left and right arrow key for the incorrect and correct actions. At the end of this study, we also asked them to do a Qualtrics survey to provide the subjective feedback. And I think I might be crossing the time, so let me know like whenever.
Don't worry at all. This is great. Like,
okay, perfect.
absolutely.
Yeah. Okay.
Just
Cool.
keep
So
going.
I'm
learning a lot.
Okay.
I agree.
You're good.
Yeah. So this is like, all right. Yeah. So we obtained around 281 responses in total, but since there are always some amount of users who does not respond or like play with the game, play with the system. So we removed all the users which had like less than 50% response rate, so that our data analysis doesn't get biased. And so we compared the error related potentials with the manual labeling in 3 different metrics. So first one is accuracy, and as we can see from this top right curve of sensitivity and specificity, we can see that error related potential based implicit feedback is more accurate over manual labeling. So it's on an average of classification of error related potentials versus non error related potentials. We have manual labeling sitting at around 63.71%, and EG based implicit feedback using the Alexander's algorithm is sitting at 80.31%. So it's definitely accurate. However, it might be non-intuitive to some users, but if we focus on this particular thing, so let's say the task is to press the left button or the right button if the agent takes incorrect action or correct action. So we, in order to provide the manual feedback, we have this tendency of pressing the same key again. So let's say the agent took 5 correct action in series and 6th action was incorrect. So we in general have this tendency of pressing the same key again even for the incorrect action, and that happens a lot, which is understandable, and which we also saw from the data that we collected during this study. Latency, I think in terms of latency, manual feedback at least as of now, wins over the EG based error related potentials, because as we have seen before, error potential takes at least 600 milliseconds. But for the fastest version of the game, which was when the agent was taking actions every 0.5 seconds, the users provided the feedback at the 200 millisecond level. So on an average 200 millisecond, they were able to provide the feedback. However, that comes at the cost of accuracy, because as we see for this particular 0.5 seconds interval, the sensitivity and specificity score is like very close to random. Like its sensitivity is around 60%, and specificity is actually very much below than 25% as well. The third metric that we used to compare the error potentials with manual labeling was comfort score. So we asked the users to scale them on from 1 to 7, and the average rating we received for for manual labeling of 1.5 second instance was 5.4, which went down to 4.9 and 3.9 for 1.0 and 0.5 seconds, which is very intuitive. However, since this was an experimental study conducted online, and we did not have, it was conducted basically during COVID, so we couldn't ask the users to wear the EG headsets and do this experiment to get the comfort score for the EEG as well. So we don't have those numbers, but since we can say that EEG based implicit feedback is more comfortable, since like it removes one extra step. Like manual labeling, people are looking at the screen, focusing on the screen and pressing a button. EEG based implicit feedback, people are looking at the screen and that's it. So it's intuitively it feels more comfortable, but we don't have any quantitative number to compare it on the same page. So our conclusion is like ARRPs are more accurate and comfortable, but they are slower than the manual feedback. However, with this thing, like it's more scalable, because if I am asking the manual feedback for a very long period of time, it's not feasible or it's not practical. However, ERRPs can be just or any brain computer interface based feedback can be just weaved into the daily lives of the human while they are like just wearing the headset, like Muse or Epoch headsets in general, and then going through their day-to-day user activities. Moving on, this is a bit on the Alexander's algorithm. I thought like I would explain it a little bit to see what is happening here. The idea is basically, actually, can I take just like a 1-minute break? So
Yeah, Mohit.
okay.
Yeah, you should be fine. Yeah.
Okay, yeah. I'll be back like in a minute. Yeah.
No worries. Thank you.
Morgan, I'll be back in a minute. Yeah.
Oh, sure. Sorry, I had to also deal with a child.
Yeah, no worries. Yeah. So yeah, just one. Okay.
Yeah, because I wanted to ask you about latency.
Okay, perfect. Yeah, I'll be back. All right. Okay, so I'll start. Okay, moving on. So here I'll just describe in very brief about how the Alexander's algorithm work to detect the error potentials. The principal idea here is is basically underpinned on the assumption that the spatial distribution and power of the signal remain unaltered for a specific mental activity, which can be captured using the covariance matrix. So from the raw EEG data, we extract epochs of 800 milliseconds or 1300 milliseconds. It's just like an hyperparameter. They're extracted relative to the pre-stimulus 200 milliseconds baseline. The epochs are used as input, where each trial is represented in C cross T matrix, and N is just the number of trials. C represents number of channels, T represents number of time samples, and N represents the number of trials. The first step is to do spatial filtering. The first step is to do actually bandpass filtering of frequency range 0.5 to 40 hertz, which removes a lot of noise. But then we also do spatial filtering, specifically use the XDON spatial filter to improve the signal to signal plus noise ratio, which is SSNR. It's another work. XDON spatial filter is another work in this community, we say research community, where filter order basically corresponds to the XDON components used to decompose the data for each event type. And then we use the covariance matrix to account for the spatial distribution of the signal power. And since it is a very high dimensional data, the spatially filtered signals are reduced to very few relevant channels. So we just decrease the dimensions of our covariance matrix using a particularly backward elimination principle based on the remaining distance. This is also one of the paper from Alexander's group and Alexander himself. And finally, this reduced covariance matrix is projected into the tangent space, allowing to manipulate features in the Euclidean space. Since like covariance matrices basically represent a point in the Riemannian manifold. However, all the machine learning algorithms that we have working so far, they work in the Euclidean space. So there is a bit of mismatch there. So we do projection from the Riemannian to the tangent space of Riemannian, and tangent space of Riemannian is approximately Euclidean. So that's why we do the projection, and then the features in the tangent space, and finally normalized and fed to the linear regression model with ridge penalty and the lasso penalties. The output of the linear regression, from there we can just like do a preset threshold by maximizing the accuracy of the over the training samples, and then we can just label the signals as ERRP or non-ERRP. However, there are some practical issues with this baseline algorithm. One is there is a possibility that the error potentials are not exactly time locked, and because as we have seen, like there could be phase jitters due to shift in user there could be phase jitters due to the packet dropping that we have seen before, but it could also be due to the user focus, which is not a variable in the experiment and is beyond our control. So this results in the reduced classification performance. So we propose some modifications in the algorithm. We still use the same algorithm, but we just change some part of the algorithm to include additional information extracted from the distribution of power across the time spectrum and frequency spectrum. So now, instead of just spatial part, we are merging the information from both the time and frequency dimension as well, which would efficiently using it, like combining all those information would, and in an ensemble fashion, would lead to a higher detection performance. And then the second idea is, now since we are using this ERRPs or error potentials at the end of the day to inform the reinforcement learning algorithm. So whenever we are not confident about whether this is an ERRP or not ERRP, we just drop it. We don't have to like provide the feedback at every state action pair, at every step of the game. If we are not confident, we'll just drop it, and that would still result in like one sample, but it would not negatively affect our human in the loop reinforcement learning architecture. So I think this whole part, so these proposed modifications has mainly two parts. One, spatial domain features and the classification remain pretty much same. Frequency domain, we use multi-tapered spectral estimation in between 400 milliseconds to 1000 milliseconds to include what is happening for the error negativity and the error positivity, and there could be some other counterparts coming after error positivity as well. And we use the frequency interval of 1 to 15 hertz. This is mainly based on the cross validation. And finally, we use the SVM based classifier to decide whether it's an error potentials or not an error potentials, just relying on the frequency domain features. And similarly, we do for the time domain as well. Like we use the power buckets every 50 milliseconds, and doing this would help us to account for a little bit of phase jitters, either due to the packet dropping or either due to the user focus. Because now if there is a phase jitter and we have like some sample coming like after 20 milliseconds or 30 milliseconds or 50 milliseconds, it would fall just into the another bucket and it will still come into as a feature for our classifier. And then finally, once we have all these three classifications, we use a soft voting based ensemble classification scheme to boost our accuracy. And even from that, if we have the confidence scores are very low, like which is sitting around 0.5, which is like very random, then we just drop those samples to so this is basically a little bit idea of how the proposed modifications improve the detection of error related potentials. So I wouldn't say like there is a very significant improvement, but we can see like in general it can increase the detection accuracy by around 10%. But if we keep increasing this parameter, which is PTH, which is like threshold measure, like it basically trades off like how much samples I'm dropping and how much accuracy I'm increasing. Because now if my PTH interval is becoming very, very wide, it means I'm not tolerating low confidence samples, which increases the number of samples that I'm dropping, but also decreases my sample efficiency. So we can see like if at PTH 0.7, like when this confidence interval is between 0.3 to 0.7, then for maze game, it could boost the accuracy around like by 18%. And this has negative effect on the sample efficiency only for the PTH 0.6 and PTH 0.7, because for the baseline algorithm that was given by Alexander, they are not dropping any samples, so they have 100% sample efficiency. And also the proposed modification architecture in which we are not dropping any samples, which is p equals to 0.5, we are not dropping any samples, so the sample efficiency is at 100%. However, at 0.6 and 0.7, if we keep increasing this interval, we are dropping more and more samples. But we can see from this analysis that even at the 0.6 threshold, the sample efficiency is still above 85% for at least 75% of the users, which makes it like really practical and universal for the subjects.
Right.
Yeah.
Just a quick follow-up question on this, right?
Yeah.
And correct me if I'm wrong. You did say that the signal was around 600 milliseconds.
Yeah. So
the latency.
Yeah. The error negativity and positivity, they both reflect under 600 milliseconds. That's right.
So for the classification, I mean, wouldn't there be a kind of a range, that you need to look for this, between 200 to 900, something like that, or you?
Yeah. So that's why normally, like I think for the Alexander's algorithm, they use after the stimulus, they use like whole 1300 milliseconds of data.
Oh, gotcha. Okay.
Yeah.
Okay. I need to look at that. Okay.
Yeah, and this is also like a hyperparameter, so which we can I think for my frequency features, I am using until 1000 milliseconds, in between 400 to 1000 milliseconds. Yeah, I'm using from 400 to 1000 milliseconds, and it's because like even these are like error negativity and error positivity are some things which we can actually visually observe, but in the neuroscience literature there has been evidence of late positive potentials, which appear like very late, so it could also inform our architecture. I think Morgan, you also had some question regarding latency, right?
Well, back a while back, you don't have to go back to the slide, but when you were talking about people at like 200 millisecond latency,
Yeah,
or manual at 200 and ERN at 600, and I was wondering how much overhead do you have of the BCI itself, like you're talking about the time interval that you're looking in.
Yeah.
like let's say at 1,000 milliseconds, you are starting your or like when does your processing start? I mean, it's real time. Is there any lag because of the processing itself?
Oh yeah. So for currently this analysis, we do not consider, because we do all of this offline, because we can always do all these offline and store like the results in the buckets. So we do not consider the processing overheads.
So you're not worried about that yet?
No, not yet. Yeah.
Okay.
Yeah. So the 600 millisecond I just use as like a just a number, reference number, because from visually I can see that error negativity and error positivity are like visually evident until 600 milliseconds. So I have to wait until 600 milliseconds to get those features. And I think there could be like 100 and 200 millisecond fixed offset because of the BCA headsets as well. There could be possible.
Easily. Just recently, I'm just kind of interested in terms of how well can we make, how responsive can we make a closed loop system, right? Because, again, like this is something that we talked about on Slack, but like in terms of neurofeedback, faster feedback is it basically can increase the learning rate, and so that's why I was kind of curious. But you're not trying to do anything real time, so that's cool.
Yeah. Currently, I'm not focused on the like real time integration, right?
Sure.
Okay, so moving on. So I think like now we talked about like how to conduct the experiments, how to obtain the error-related potentials, even how to detect the error-related potentials. Now the second part is how do we integrate these error-related potentials-based feedback into the reinforcement learning algorithms. And I should add that I'm presenting like this particular part of work just for the sake of completeness, but all this research has been done by my collaborators, Dozu and Professor Farmars Fakri. So as we have seen before, DQN learning, it learns this optimal Q value function where we provide this reward, which is like RT plus 1 as the reward that is coming from the environment. Now what we do is we do reward shaping. We provide RT plus 1 plus R dash T plus 1, and this R dash T plus 1 is obtained from the human feedback. So R dash T plus 1 is set as like minus 0.75 if it is an ERRP. So it means that I'm adding negative penalty whenever there is a error potential detected for that particular state action pair. Otherwise, I'm using it otherwise I'm providing only 0. So that this acts as this augmented human feedback. And this simple negative reward shaping, their research says that it preserves the policy optimality, which means that adding this reward function does not change the behavior of the agent in a suboptimal manner. So what it means is that the agent will still learn the optimal policy or the optimal way to play this game environment. However, now it will just learn it faster. So now we can see this DQN plus ERRP in the action. So for this particular task, what we did was, I think as Morgan was mentioning before, we processed the ERRP buckets in an offline manner. So we process the ERRPs, we store it in buckets, and while this agent is training or like executing these actions, then we provided these ERRPs online directly. So all this ERRP processing happened before the agent started training. So that's why like we don't have to deal with any of the practical impediments with development issues, a real-time human feedback loop system. So as we can see from this, it works pretty well. And then the way to quantify it is how much acceleration are we able to get. So we are able to get like around 1.75 times acceleration over the averaged over the 5 subjects, and it could go in between 2 to 3 times. I think we did also sensitivity analysis of how much accuracy of how much accuracy is needed for error potential classification accuracy in terms of seeing the acceleration for this human in the loop reinforcement learning agent. So for example, we can see that if we are not providing the any ARPs, we are sitting at 170 complete episodes it takes to learn the optimal way to play this game. However, we can see that if I am like other extreme, like if my accuracy, ERRP classification accuracy is 50%, then it increases the number of episodes, which is like basically harming the reinforcement learning algorithm, because now the human feedback is bad. Like it's a bad human feedback. It means like randomly I'm just saying like you did right or you did wrong, which makes it more difficult for the RL agent to learn what is right and what is wrong. However, like the main thing I think I wanted to focus here is with the state of the art algorithms, which sits around like 70%, the learning acceleration achieved is like around 1.22 times, but which can be increased to around 1.8 times or even more than 2 times if we boost the accuracy to 80% or more than 90%, as we have seen with the modified error potential decoding algorithms. However, okay, so after presenting all of this, there is still a little bit of problem in this environment, problem in this research, which is basically the supervised learning of error potentials. We are using the labeled samples from user trials, which means, let's say if I'm training the error potential classifier on the maze game, it means I'm using the labeled samples, like what are the correct actions and what are the incorrect actions in the maze game, to provide the labels for the error potentials. And if I have those labels as it, like which states are correct or which states are incorrect, I don't need the human feedback. Like I can provide that information directly to the reinforcement learning agent, and the reinforcement learning agent would be able to like accelerate its learning by itself. So this basically is one of the key distinction between ERRP plus reinforcement learning work that has been done before versus what we have been doing. So what we did was we show that can these error related potentials be learned in a very generalizable manner, which means I learn it for a very simple environment. So I talked about 3 games: wobble, catch, and maze. So I train my error potential decoding classifier on the wobble game and catch game. And then can I use this trained classifier to classify the potentials that are coming from the maze games? So now I can assume that for the wobble game or for the catch game, I know all the information because those environments are simple, those environments are known, and the what actions are correct, what actions are incorrect, is that information is available, which helps me to obtain this labels for error potentials and train my classifier. But for the maze game, I don't know what is the correct action, what is the incorrect action for these particular states. So can I use this error potential, which is trained on the simpler games like catch or wobble, and use it directly on the unknown and complex environments? This is the very exciting part of our research, and then we show that there is a visual evidence of transfer learning for these error related potentials. So I think this was one of the picture that I wanted to show in one of my previous slides, which got corrupted. So these are the error potentials that we can see are coming, and we can see that there's a error negativity coming around like 400 milliseconds, and then error positivity coming around like 600 milliseconds. And visually there is an evidence that these error potentials similar, and which makes sense intuitively because the error related potentials are not tied to any situation or any environment. It's just like the generalized notion of error detection, whether someone committed an error or not. So it should not be dependent on the game environment or like the subjects or like the other environmental conditions, and which we can see roughly from these waveforms, and these are averaged waveforms. So what we did was we tested on the samples that are collected from the maze game, but we trained our classifier only on the samples from catch and wobble game. So we can see that definitely there is a little bit of reduction in accuracy. However, still we are able to decode these error potentials in a very feasible manner or very reliable manner. And we compare basically how the transfer learning approach performs well, works differently between between proposed modifications of the algorithm and the baseline algorithm that was presented by Alexander. So that was one of the, and then here at the end, we also provide the whole comparison of generalizability, like all permutation combination of, like if I train on catch and test on maze, what would be my accuracy? And so this orange lines basically represent the training and testing on the same game. So if I train on the maze game and test on the maze game itself, this is the highest accuracy I would achieve, like 84.4%. But if I want to see the generalizability of the error potentials, then I'm training it on the catch and wobble game and testing it on the maze environment. Then I'm getting like around 70.9% accuracy, which is like around 80% of the variance I'm able to capture even with the generalizability. And this is currently active area of research going on in our lab, where we are trying to improve this generalizability result and see what are the potential things which affect this generalizability. So currently these are like four particular dimensions we are working, like, which is scaling our environments. Like, can we build like more complex environments? Like, these are still reasonably the environments that we developed were still reasonably complex, but can we use the same technique on the off-the-shelf Atari games like Pong or Space Invaders, and also apply this whole research in the real robotic environments? And the second dimension at which we are considering, and most particularly our collaborators are focusing on, is the consideration with reward shaping. Like, what are other possible approaches to integrate this human feedback? Like, there must be some more optimality in this, and how we are integrating this feedback. Currently we are just like adding this feedback with the environment reward, but can we do better? The third is, I think, what Morgan talked about, like which we do want to build at the end of the day, which is hybrid fast learning with real-time human feedback. How can we agent would be able to play the game at superhuman speed, but in real time we would be presenting the game at only 60 frames per second. And then we want this whole end-to-end system where the humans are able to provide the feedback in a very real-time manner, and the agent would be able to learn from that. So it has a lot of research challenges as well as development challenges. And the fourth is a very interesting, I think it's a very scientific research part, is like do a deep dive on the error potentials. Like, I want to understand I want to understand these ERRPs as like as the concept. Like, what are the other variables which affect the ERRPs? Like, are there any system kind of variables? So for example, like if my agent is moving fast versus agent is moving slow, or the generalizability or transfer learning, what is the area of generalizability? Like, can it generalize over trials or sessions, or like games, like from catch game to maze game, or like from catch game to any robotic environment, or like even users, like my error potentials versus Morgan's error potentials, like how they're different, and can a classifier trained on my error potentials would apply directly to any other user? So these are the current research questions that we are trying to answer, and that is basically the end of my presentation.
That was great, Mohit. I really, really got so much from that. And I also just don't think I've had such a clear explanation of deep reinforcement learning.
Yeah. Thank you. I tried to like cover a little bit of reinforcement learning, because I thought like if I don't touch that part, like it's really hard to understand the motivation of like why we are doing this. And to understand like that motivation, we need to understand like how reinforcement learning fundamentally works, and like what are the caveats or what are the problems with the reinforcement learning.
It's perfect. It's perfect. So yeah, I mean, like you've got a problem, or certainly for those who haven't used looked at event related or error related negativities before, this is typically where you've got this task, and the person, I mean, basically you don't get an ERN necessarily for every mistake that the person makes. And
yeah,
and so so I mean, I feel like you might, if you if you're using as your bar like every kind of like misstep that the agent makes, like you'll never get 100%, but because like the person might not actually have an ERN kind of response to each of those things, right? But so I mean, that's one issue, but at the same time, like I love what you're doing with it, and I'm curious, I mean, like, so does that mean that you're not trying to use, like, I mean, if you are doing everything offline, or certainly one of the reasons I thought you were doing everything online was that you weren't using ICA and things like that. Like if you're doing it offline, then why not throw all sorts of tools at cleaning up the EEG first.
Right. I think, yeah. So so even like in that particular domain, I think like I have like that IEEE Allerton work, like blink algorithm, which basically detects the blinks. However, like when I analyze, like I'm definitely sure like it would, like, but my hunch was that it would impact the accuracy like 2%, 3%, or 4% kind of thing. So my focus was on like how can I improve the like algorithm in a more fundamental manner, because like as a PhD student, it also is like I have to think like what could count as the research contribution versus what could be like just like an addition in terms of improving my accuracy. So
I'm not sure that goes away when you're not a grad student. Like I think that's always going to be the problem.
Exactly, yeah, that's always the problem. Like it's like if I spend like 3 months or like 1 or 2 months like working on something, but it doesn't count as the research contribution, like is it really like worth it? So yeah, that's, I think that was one of the things. But yeah, definitely I agree with you. Like we can throw a bunch of tools with that for this offline processing to improve the ERRP detection performance.
Yeah, I mean, I guess I'm kind of wondering, like, if you get up to, 80%, 85%, like, again, because I don't know how much, like, a person, is going to have that ACC activation, like every misstep, and some of it's, I mean, there could be a number of factors, right? Like is the person actually paying attention at that point? Like do you want to make sure with eye tracking that the person's actually following the agent, and if their eyes start to wander off, and then reject those missteps, and potentially improve your accuracy, just because it's like there's no point in including trials where they're not even looking.
Right, I agree. Yeah.
But at the same time, like I love it, and I'd love to see. I mean, well, I put a link in for Spinning Up, which is OpenAI's reinforcement learning kind of like educational workshop program. And to get you, it's a way to get started with OpenAI Gym. I'd love to see, DeepMind, or, what would it take to be able to move to kind of like a first person, not necessarily like DeepMind Lab basically uses the Quake 3 engine, and you wander around in a maze, right? But it's kind of, I mean, so like honestly, the actions are still very limited, but it looks more realistic in a kind of 8-bit sense.
Right. Yeah.
How much would it take to move, or move your environment into something with more complex? I mean, there's something, well, like putting, then the person's kind of like, it's like they're wandering the maze. I don't actually, if you kind of, they need to really see the whole, it's because they've got knowledge of the whole map that actually is kind of what's generating their ERN, isn't it?
Yeah, exactly. Yeah, because the human observer like knows exactly what is going, like the way to play this game, or like the way to act in this environment, and that's what, like, so that's actually an open research question I was having in my mind was, is this like actually ERN, or is this like expectation mismatch? because I have like an expectation from the agent that agent should do this. So it could be both, or like it could be just one of them, or it could be both. But I did not include that in my slides because I was just like working on it. But I did some analysis of like, like just trying to see where this waves are coming from. And from this analysis, I saw that like at least like I see error negativity coming from the ACC, which is like high activity on FPZ and PZ electrodes as compared to any other electrodes, which makes sense because like ACC is situated as like right below it.
Yeah.
But I think there are like so much to explore even in the domain of error related potentials or like any ERNs. As you mentioned that not 100%, like if the agent is making mistakes like at every step, the human ACC cortex will like stop lighting up because it will not light up like after like 10 or 15 sequentially done wrong actions. It won't care. It will give up. But like, so that's why like the way that we designed these experiments were like we made sure that the agent is taking wrong actions with like some only 20% error probability.
Yeah.
So incorrect actions were taken only like 20% of the time, but most of the time like it was taking correct action. So this event of incorrect actions becomes comparatively rare as compared to the event of correct actions. But yeah, there is like so much to explore, even just like basic psychological and like the neurological aspects of the error related negativity.
Yeah. I used to be, or it's funny because the company that I used to work for that was also a research EEG, company, the principals were kind of error related negativity researchers. So Don Tucker and Fan Liu.
Oh, that's cool.
Yeah. And so we would see a lot of those. I mean, we'd see a lot of those experiments, and as I'm sure in those experiments, you have like 200, 300 trials, but then, the actual number of error related negativity trials is variable and is small.
Very small. Yeah, I agree.
Right? And well, so, I know that, or like, certainly have thought about how this could be used in robotics. I mean, like not so much like, would it be easier to have, I mean, I like this idea of using the ARNs in the sense that like really capturing especially non-invasively capturing motor activity to control with, good granularity to control a robot arm is hard. But to tell when that robot arm is about to knock over a cup, like that I might be able to get from the person,
right?
But so in your offline process, I mean, do you have any guess of how slow you would be? Like because like 1,000 milliseconds might be too late for that robot arm to stop that robot arm from knocking over the cup,
I think like this part, like I think the part of the time which takes a more time for the ERP detection is the offline training part. So like when I'm training training my decoder or like the classifier, but when I'm just classifying the test samples in the real time, I just have to do a bunch of metrics computations, which can be done like very, very fast because
that can be done super fast. Yeah.
Super fast. Like just, I think like my rough estimate would be like less than 10 milliseconds. And definitely it depends on like the computing power that we are using, but considering like even like our smartphones these days work on gigahertz level, so
sure. Okay. So, I mean, so then really it's down to, I mean, again, like your example is perfect, or your example is perfect for looking at this interaction, right?
Yeah.
I mean, and that like it's awesome. I am curious about, how well an ERN would move over to the real time where you've got to wait for this brain, you've got to wait for the brain activation.
Yeah.
And so that adds a delay that's at least 400 milliseconds. I mean, I want to say like, yeah, okay, yeah, but still, it's great. Does anybody else? Don't let me hog the question. Anybody else got questions?
Yeah. No, Mike, it was actually good. I definitely learned a lot. When you talked about, I don't know if you brought up this at all. So you can actually have an execution error and an outcome error, right? So I mean, did you maybe did you have to measure the delta waves or the theta waves at all, or can you did you put some topographic visualization into that as to see where the delta waves are actually getting amplified as a result of outcome error at all? Do you know what I'm saying?
Yeah, I agree. I think I did plot the topographic maps. I just didn't put it in the presentation, but yeah. But I think like in terms of the delta waves, I was mainly concerned about like using delta waves as another measure to see like if the user is focused on that particular thing or not. That,
Exactly. Okay.
that was my purpose of like using delta waves. But that was like kind of thing that always remained in the to-do list, but I never like actually worked on that particular part because it was still coming in the bucket of like how I increase the decoding accuracy of error potentials.
Right. Okay. Cool. Oh, great. Thank you. Thanks for sharing. Yeah. And did you say that there is a preprint on this, or it's?
Yeah. So check the meetup agenda. I've got links to Mohit's website,
Okay.
his Google Scholar, his archive, or the archive paper he's co-author on, and a few other links, I think. I think I took off Blink and Cerebro, but I still want to I'll give you time to finish up your PhD, but I still want to have you come back and talk about neuromarketing and how well that potentially does work.
Yeah, definitely. Like, yeah, I think I would love to like come and like talk about my research work at any time. And neuromarketing, I think it was a very small project, so I like it was more like a like just exploratory project for me, like to see whether like how much we can contribute in there. But it's definitely tougher because like those potentials preferences are like very noisy as compared to the error related potentials or like any other ERN.
Yeah. No, I'm less. I mean, like I'm just interested in how you approach it, because honestly, I think it's like a thankless problem. Like it has no good solution.
Yeah.
But I love the name of the project in that Cerebro. Yeah. So like I want to just talk about a few other things, but I was very happy to have you present the whole thing. And so how much of this code is available? I listed your GitHub as well. That's where people can also find Mohit's EEG. Was it data? Yeah, it's just data. Yeah. So how about this OpenAI stuff, or like just the
I have pretty much everything available. Like I try to release like all my codes and most of the data sets, like even like the Blink and Cerebro. Cerebro, I think I used the data from another author, so I could not release it by my own. But Blink and the ACM Chi papers, I've released the data sets and codes. And even for this particular project, we don't have the data out yet because we are still like working on it, but we would be releasing the data soon. But other than that, I have like all these environments that I talked about: Wobble, Catch, Maze. All these environments are available on my GitHub. This algorithm, the proposed modifications of the algorithm, like which I presented, like how do we improve the decoding accuracy of error potentials. That code is present. That code is present publicly. It's publicly available in the GitHub. And yeah, thank you. It was, I think, my pleasure. Like, I really loved like coming here and talking about it and getting the
It's cool. It's cool.
feedback from community.
Yeah. I'm curious because it's super interesting. I mean, I think you could have people watching a lot of games and just seeing what they pick up on. But the fact that you've got EEG with these ones, I think is really intriguing. And no, I was going to ask one other thing, but I'm blanking on it right now. Yes. So, like, could we? Well, I mean, you're using OpenBCI. We use LSL to do the time synchronization.
Yeah.
Is that what you're using? Like, when you say TCP/IP, I know that OpenVibe definitely like does some things, but that's not equivalent in this case, right? To LSL. It's actually like opening up a port and doing some sort of just traffic.
Right. Yeah. So I think LSL. I think like when I was trying to figure out this, LSL is mainly try to like add the synchronization because we have to add like something on the OpenBCI hardware, right?
You don't have to add anything in the hardware. I mean, so that's the good thing is that make a quick pitch for EEG notebooks and just say they support OpenBCI headsets. And are kind of like I said, like it's integrating in our case with PsychoPi projects. Okay, so PsychoPi, and I think they've got some. I think there's some Pi game examples, and so I'm not sure from the OpenAI side, or like basically it's an Atari emulator, right? How hard it would be to be generating an LSL stream, but basically, yeah, it's like once it's made that connection, it's basically passing what it thinks the clock offsets are, and that that's the synchronization bit. I don't know if is Jaden with us. No, maybe not. But anyway, we'll. I mean, I definitely want to talk more. I know you're on OpenBCI forums, or I've seen you on OpenBCI forums. Are you on Slack, NeurotechX Slack?
No, I don't think so, but I'll join definitely. Yeah.
Okay. I mean, no pressure. But very, very interested to keep the conversation going because I mean, I certainly, for one, again, because you used Muse and OpenBCI, those are the big devices that we're using. And to see things like Blink, even, I mean, or just like common sense algorithms to improve the devices that we're using. Great.
Yeah, Morgan, just a quick question, right?
Yeah.
Sorry, this for Morgan. I'm sorry, you brought up lab streaming layer. How prominent or how popular is lab streaming layer? I mean,
it's very, or I want to make a bit of a pitch for it, even though like one, it's manufacturer independent, right? So it started out as something that Christian Kota, I believe, was first using it at the Moby Lab in Berlin to synchronize a bunch of wearables, and it's like NTP based like synchronization, but then he adds there's a bit more to it, right, with this kind of like publish and subscribe layer that LSL is also generating. And again, like part of that, and I've had this discussion with Andrei Parfenov, the BrainFlow developer. you know, because he's like, well, I don't see why you need LSL. I'm like, well, because you're always collecting data from one device, right? Like if there's 4 separate devices on the person and they're all wireless, right? Like, how are we going to synchronize all this? You know, so you end up with something that's going to look a lot like LSL. And you know, or you've got to do what researchers do, which is like somehow simultaneously trigger all of those electronically, right?
We recently started using that. I don't want to take too much time, but you know, in addition to EEG, we are also trying it against HRV, like a Whoop.
Yeah.
So it's you know,
Sure.
yeah.
I mean, you know, so people are doing, you know, EMG, HRV, GSR, you know, EKG. Yeah. I mean, there's a lot of, you know, and these can all be separate devices, right? You know, if you throw on NIRS and like you want to capture all the physiological confound signals that NIRS includes, right? Then it's like you've got your NIRS plus your EEG, right? But then you need like a strain gauge for respiration and pulse ox just to catch, you know, I mean, you know, things like EKG and things that you need to do your signal processing of your NIRS. I like it. And then Brain Products, I think, was paying. So one manufacturer started actually using it in their, like, directly in their tools, and not that they co-opted it, but like I think Brain Products actually put a lot of resources into LSL. And I like I said, I've said this before, I really recommend Lab Streaming Layer Slack. If you've got to be on Slack, and I wish we weren't, because we just lost a lot of our message history because we're on the free. You know, I really recommend the Lab Streaming Layer Slack, because Chad Boulay, who's the current kind of like maintainer of the GitHub project, has a lot of really smart, insightful comments about you know, about the kind of work that we're doing and about programming. So, you know, yeah. So, and I think he's at I mean, he's definitely at a neurophys lab in Canada, but doing some cool stuff. Anyway, they maintain it. You know, so it's like it's got a pretty active, you know, set of contributing developers. You know, I don't feel like it's going to fall to the wayside and atrophy, or, you know, not get updates. I've got some issues. If anybody is listening to this and has LSL working on a Raspberry Pi, I know some students that would be really interested if it was a simpler pip install of, say, Muse LSL, or even just Pi LSL. Yeah, I think it's good. Or, you know, the replacement for it would be something that just can somehow improve the accuracy of the synchronization, or even better, handle what we want to do, and somewhat relates to what Mohit presented, which is we want to have 2 people playing something like Quake or Doom, but then be, you know, across wide area network as opposed to local area network. So like hyper scanning, but that's managing to somehow, you know, I mean, basically, if we control the game server, we would know a lot about, you know, what the central time is. But you know, how well can LSL scale to WAN as opposed to LAN, which, you know, is going to have some additional problems. But you know, again, like if you set up the game right, and ask very specific questions, then you can make the lag or the inaccuracies in the synchronization not be so important. It is 9 o'clock, which is technically when we end. I want to just very quickly check what I put for the last hour, which I said I was going to cover. And so, sorry, I just wanted to cover what is going on tomorrow and next week. I've lost.
Morgan, can I take a minute?
Yeah, please.
I just wanted to say thanks because it's kind of midnight here. So
No. Yeah. Absolutely. Anybody on the East Coast who stays to the end, you're a hero. But thank you so much for joining us, and hope to talk more later.
Definitely, thanks for providing me the opportunity to speak here, and I would love to come back again and learn also about the cool things that this community is doing. Yeah,
great.
Thanks again.
Great. Thanks, Mahit. Okay, so so IROS has been this week, and Jaden posted what will probably be the paper for next week's Neurorobotics. That's Tuesday at 5 p.m. Pacific time, and we didn't spend 1 minute talking about Neuromatch. Good night, Santosh. So much to cover there, and that we'll need a month. So I made like I said, I made a if you do join BrainHack or BrainHack's Mattermost discussion board, there is a NeurotechX channel. And I hope that we start planning for what we could do for BrainHack Global 2020, which is starting November 30th to December 14th, I believe. So there'll be a number, there'll be local events going on, but all under the BrainHack Global banner. And I think we should definitely support EEG NIRS related ones, amongst other things. And so kind of tomorrow and Saturday would be the last days for any kind of Neuro Hacktoberfest contributions. If we're but don't forget you could get a T-shirt, and there was a great webinar. I mean, again, I very much recommend this BMI webinar that IEEE Brain had. You can find links to the webinars that I don't know if those are going to be free for non-IEEE members. So apologies for that. But they do have a pretty active YouTube. The cerebral organoids digital course was just incredible, but super highly recommend the Frontiers paper that I got there listed right after it, as a great overview of what's going on in stem cells and cerebral organoids. We'll hopefully be able to focus on cerebral organoids and recording electrical activity from them with multi-electrode arrays at some point, because it is just exploding. So tomorrow there's 3 meetings. BrainSpace Initiative. They are covering a paper which I don't know why it's not listed. They're saying the next talk is November 6th, but I thought there was one tomorrow, and sometimes this homepage is not up to date, so I don't know why that is. But anyway, definitely check them out. If not, check it out November 6th. There's the Neurophotonics mini symposium and the Learning Salon, which is 1 p.m. Pacific time. All great meetings. The Neurophotonics one be somewhat animal based, and so next week, check out the neuromorphic computing and the worldwide theoretical neuroscience seminars online. In addition to getting ready for next week. And we will be talking more about time domain nears. And thank you so much. I want to thank our videographers, Ryan and Alex. And we'll see you next week.